All right, so now we get to the third and final part to this handout, where we talk about actual composite functions, or the composite operator, I should say. And that is when one function acts on another function. And we're going to use the open circle. Remember, I was talking earlier about the multiplication dot, and you don't want to draw it as a circle. Well, this is the reason why. It'll get confusing if you try and do a bigger dot. And that actually does mean something else mathematically, but we're not even going to begin to get close to that. So just for right now, just do a dot or an open circle. That is all you have to worry about. And so f composite g of x, is how you'd read that, is the same as f of g of x. And so let's go ahead and write all that out. So this would be f composite g of x equals f of g of x. Right? That's two ways of saying the same thing. Right? So that is these are the symbols. This is how you would read it out loud. So the domain is the intersection of the domain of g of x with any new domain restrictions that arise from the resulting expression. All right, so let's go ahead and put that into play. Here we've got f and g. Note that g has a domain restriction that x must be equal to or greater than 1. Right, because if it's less than 1, we'll have a negative number. So f composite g of x is simply f of g of x. I'm going to be taking this g of x term and shoving the whole thing inside of f, right? So wherever I see x, I'm going to replace it with a g of x. And so this will become g of x squared plus 1. Or simply x squared plus 1 x minus 1 quantity squared, whole thing square rooted, quantity squared, and then plus 1. It's a little messy, so let me go and rewrite that. So we've got the square root of x minus 1 squared plus 1. All right, so the square of a square root is just what's inside. And so we end up with x minus 1 plus 1, which is the same thing as x. But note we do have the domain restriction from g that x must be equal to or greater than 1. And that's just what the domain is. 1 to infinity. So if you were to graph this, which I'm about to, just the graph of x starting at 1, filled in circle, and then it's just y equals x to the right, nothing to the left. And that would be the graph. Moving on. We have the example 1 over x for f. G is 1 over x plus 1. We're calculating f composite g of x. So note that because g is being stuffed into f, we need to worry about the domain restriction here, but not necessarily in f. So here we see that x cannot equal negative 1. Why is it negative 1 and not 0? Pause the video and ask yourself that question and see if you can answer it yourself. The reason x cannot be -1 is because if x is -1, then I'm dividing by 0. But note that if x equals 0, I'm dividing by 1. I can divide by 1 all day long. It doesn't matter, right? So x equals 0 is fine. X equals -1 is not. So that's our domain restriction going in. And so we've got f composite g of x, which is the same as f of g of x, which is the same thing as f of 1 over x plus 1, because that's what's being stuffed in there, right? As a reminder, x cannot be -1. And so we got 1 divided by 1 over x plus 1, right? Because this x is being replaced by g. And so this is the same thing as 1 divided by 1 over x plus 1, or 1 times x plus 1 over 1, which is simply x plus 1. Don't forget our domain restriction that x cannot equal -1. And that would be our final answer for that one. Okay? Moving on. We now have, again, it's f of g, so since g is going into f, we got to think about the domain restrictions here. G has no domain restrictions, so there'll be no domain restrictions being moved forward. So let's go ahead and write this out. F, and you should be saying this aloud with me as I'm saying this, f composite g of x is the same as f of g of x. And what is g? G is x plus 2 in this case. And so that's what I'm going to plug in here. So x plus 2 plus 1. And that'll be the same as 1 over x plus 3. Now, I don't really need to write the domain restriction on this one because it's evident from the expression itself, right? X cannot be -3 because if x is -3, this expression will simply not exist. And so our domain goes from -infinity to -3. Union -3 to infinity. Okay. So let's do some graphical examples here. And this is mainly just to remind you guys, this is how you read a graph. I'm sure you guys know how to do that, but we're just going to run through this as an exercise. What is f of 0? All right, first we find f. When x is 0, f is 3. And so we got 3. And then h is 0. Note h is a constant function, so that'd be -1. And so our answer here would be 4. And here we have h minus f of 2. Say that with me. H minus f of 2. And so we got to find h of 2, which of course is -1 because h in this case is a constant function. And then minus f of 2, which is 3. So -1 minus 3, that would be -4. And now we have h divided by f of 0. So h of 0, of course, that's -1. And then f of 0, that's 3. And there you have it. The answer is -1/3. And now we do the composite function here. F composite h of 3 equals f of h of 3. And so what is h of 3? Well, h of 3 is, of course, 1. And then what is f of 1? Well, that would be what you see right here. There we go. Okay, so let's do some more examples where we use everything we've learned so far. We got x squared and x, and we want to find f plus g and its domain. So f plus g of x is simply x squared plus x, and the domain is all real numbers, right? There is no domain restriction here. Okay, so pretty straightforward. Okay, so next page. We've got these two functions, and I'm subtracting g from f. Note that in both cases, f or g, x cannot be positive 2. And so let's go ahead and find f minus g of x. Well, that's going to be x squared plus 1 over x minus 2 minus 1 over x minus 2. So 1 over x minus 2 minus itself, that's 0, leaving us with x squared, just x squared, not so fast. We got to remember our domain restrictions. X cannot be positive 2. And so this would just be a standard parabola going through the origin, but you'd have an open circle whenever at the point 2, 4. Right, because when you plug in 2, you'll get 4, but you won't plot that point. You'll put an open circle there. So it would look something like this. This open circle there. All right, there we go. All right, next one, we've got f divided by g. Note that g can't equal 0, but that doesn't matter because 1 over x squared will never be 0. But inside of g, we've got 1 over x squared, and g has a domain that it cannot be 0. So that's something we're going to have to keep in mind, possibly. It will have an effect. And so f, that's on top, x squared. G, that's on bottom, 1 over x squared. We'll note that this is the same thing as x squared divided by 1 over x squared, which is the same as x squared times x squared over 1. X squared times x squared, that's x to the 4th, but with the caveat that x cannot be 0. And there we go. Next example. Now we're doing the composite function. And so we got to bear in mind the domain restriction of G. Here, x cannot equal 2. And so f composite G of x is the same as f of G of x. And so G is simply 1 over x minus 2. Right? Wherever I see x and f, I replace that with x minus 2. 1 over x minus 2, I should say. And so this becomes 1 divided by 1 over x minus 2, which is the same as 1 times x minus 2 over 1, which is just x minus 2 with the caveat x cannot equal 2. Okay, and there we are. That's the answer there. And now, final page. And we have x squared and the square root of x. Note here, x must be equal to or greater than 0. And so f composite G of x is again the same as f of G of x. And G of x, well, that's the square root of x, like so. And so I've got the square root of x squared, which is x, such that x has got to be equal to or more than 0. That's our answer with the domain restriction. Right, the domain here would simply be 0 to infinity. Moving forward. I want us to keep this example in mind as we move forward, because note the difference between these two examples is simply that f is now the square root of x and g is now x squared, still finding f composite G of x. So let's see how this pans out. Will it be the same or will it be different? So we have f composite G of x, no domain restrictions on G. So this is the same as f of G of x, and G is now x squared. And so I'm going to be plugging that into here. And I take the square root, so that takes care of the square. And you might say it's just x, and I would tell you not so fast, because there is a little trick going on here. What happens when I just plug in x? Like if x is a positive number, it stays the same, right? That's what the identity function means. But what happens if I plug in a negative number? Well, negative number gets squared here, making it positive. And then when I get a square root, I just get the positive number back. So what is happening here is that this has become a de facto absolute value. And so here is the absolute value of x, whose graph, as you know, looks like this, which is different from what the graph would be from the previous problem, because that would simply be just one right side. Here we got both sides, but it's absolute valued. Okay, so we've stumbled upon another definition of the absolute value function.